Hello, everyone. Welcome back to NSX for audio tutorial. My name is Danny. So in this lesson, we're going to talk about NSX switching, which is very important for the exam and also for the knowledge of NSX. Let's jump right in. Within this today's lesson, we're going to go over data plane. What is a data plane? What is transport node and a transport zone? And also a lot of terms we will cover. And also we'll give you a switching structure or some of the data center or profile, which support a lot of switching functions. So let's get started. For the VCP NV point of view, we have a lot of objectives related to switching. So if we look at the blueprint, we have a object 3 2.5 and talking about logical switching, 2.6 and 7. A lot of chapter and objectives are related to the switching. So let's go over a lot of detail and get into that. So in the previous lesson, we just talked about a data plane where there are 3 planes, remember? So one of the important plane is a data plane, which is a distributed data plane. So we just told you that in vSphere environment, data plane equals ESSi host. So here we just want to cover the term transport node. So what is the transport node? We just simply cover this in the last video. Just give you a recap here. Transport node. So if you already remember what it is, that's a perfect. So transport node is a node which is responsible for forwarding data plane traffic originating from VM, container, or some other upper layer. So there are 3 form factors of transport node. So for ESSi host, in terms of the type of virtualization we use, we have ESSi host as one type of transport node. We have bare metal, KVM, also another hypervisor, and also bare metal. We support Linux and Windows. Remember that I told you last time. And then also a particular or a special type of transport node, which is edge transport node. Okay. And speaking of terminology or data plane terminology, we have a lot of terms. Here we are covering some of them. One is a NVDS. So I remember I told you a lot about NVDS or VDS 7.0 with NSX. So its function and its components. So here we already talked about MPA and RCP sort of things. And also just remember NVDS is a virtual switch within the transport node, or VDS7 or VDS with NSX are another type of virtual switches inside of the transport node. That's the meat of transport. That's the meat of virtual switch or NVDS. There are a lot of features on NVDS or VDS with NSX. We'll get into that a little bit later. Okay. So just remember, or just please note that here, when you look at the transport node, or when you look at the NVDS, and every NVDA has its attributes, which is a name. Key value name is equal to production. For example, a name is lab. So NVDS for VDS 7.0 has its name. So we can use this name, or this attribute as an index for further data structure. Okay, so from other side, from other perspective of transport node, we can see that transport node. Here we just show you the what is a transport node is like, or what a transport node look like. So just mean that, for example, here is a ESS host, so also called a transport node in NSX world. So for a physical server, they have to have some NIC or physical NIC, right? Physical NIC, PNIC, or physical NIC. So we recommend you have, or the physical server, a physical server has four PNIC for NSX deployment. That's the best situation or best criteria for you to install NSX or design an NSX system easily and very efficiently. So why we recommend that recommend being a 4 PNICs. So for here, for example, we have two types of connection, physical connection. One goes to a management plane or management uses. One blue one goes to, or is going to the VM workload traffic. So for redundancy, you have two, right? You have two, a physical NIC for management usage, and two physical adapter or physical NIC for VM traffic, for blue one transport traffic. So I just recommend you have 4 PNIC. That would be the best case. And here we have a TZ term, a term named TZ. TZ means is a collection or the group. A TZ defines a collection of transport node who data communicate with each other across physical infrastructure. That means that if you, let's say there's a data center, you have 10 physical server, and you just want 10 physical server to communicate each other, to talk to each other as a group. So that means that you have a collection. You have a collection of 10 physical server forming a transport zone. This is transport zone. the same similar one as illustrated here. So here is a TN2 or TNN to TNN. So you wanted them to communicate or to talk with each other. So you have to put all of the transport nodes into a group to form a particular TZ. Here in this case, is the TZ name is TZ1, and also have the same NVDS name, which is production. So that means we have a term, or we have you can see this is an area or territory for the whole physical server who want to talk to each other. That's the TZ. So for TZ, we have two types of TZ. One is overlay, one is VLAN based, just VLAN TZ, one is overlay TZ. So overlay TZ, that means that overlay TZ include a overlay transportation or traffic. The VLAN TZ only includes a VLAN-based something or VLAN-based segment. Just we'll talk about it segment a bit later in the next slide. So I just show TZ types, overlay used to internal tunnel for transport node. So carries Geneve encapsulation traffic for overlay traffic. VLAN is carry AO2.1Q, traditional VLAN tagged traffic. That's the two types of transport node. And here we have another term, which is tunnel endpoint. Tunnel endpoint. Remember, I just mentioned that we are creating or building a tunnel, just like a bridge. Every tunnel has its head and toe or end. Every end has to have a TEP IP address tunnel. So TEP IP addresses, TEP IP, here we also have a TEP IP. So every tunnel has two TEP. One is for the head, one is for the end. So how can we get this IP? So we just are leveraging the IP pool, IP address pool, to assign IP to every TEP or to every tunnel end or every transport node. So for a transport node, every transport node needs at least one TEP IP for overlay traffic. For example, here is a TN, here is another TN, right? So you just wanted a VM sitting on this TN, talks with another VM sitting there. So they have to have a tunnel. So that means this TN has to have a TEP IP, and this TN also have this TEP IP to form a channel, to transmit or to transmit the traffic through the tunnel. Yeah, that's a TEP and IP address pool configuration. So let's talk about segments. So we already saw what TZ is. So within the TZ territory or within the ATZ, we can create segment. Segment, formerly known as logical switch, or as analogous to VLAN subnet, roughly, VLAN subnet, roughly. So segment or logical switch is virtual layer 2 broadcast domain. You remember broadcast, layer 2 broadcast domain when you learn fundamental the layer 2 switching knowledge. And also VLAN, if you talk about VLAN, VLAN is also a type of layer 2 broadcast domain. So here we just want to give you an explanation on this diagram. So we have a TZ named TZ1. In this TZ1, we have two segment or logical switch. Our logical switch 1, overlay logical switch 1 is yellow 1. Expand the whole TZ, expand to whole TZ, right? And the brown one, logical switch 2, also expands there to the whole TZ, around the whole TZ. So that means you can create segment, one or more segment within the TZ. So a segment never go beyond the TZ area, right? For example, LS1 and LS2 never goes out of the TZ1 and to this area, to this transport node, never. So just a maximum territory or maximum for the segment is their own TZ. Okay. That's a segment. So on every segment, we have a lot of VM workload. We have a lot of workload assigned to or attached to this different particular segments. So that means we are building up the layer 2 cabling virtually. So segment, the concept of the segment is pretty important for you to design the whole NSX system in terms of layer 2 switching or network topology. So for NVDS, for this type of virtual switch, we have, or just VDS with NSX. We have two types of virtual switch. Commonly, we use standard type. There's another one in enhanced data path type. Enhanced data path type is for high performance forwarding or for service provider to implement their NFV function. So if you just remember, if you look at the NFV, a service provider, and high performance words, pretty highlighted words, you just reminds you that there's a enhanced data path type NVDS. Now here is a configuration sample. When you create NVDS, you can just select standard or enhanced data path. Generally, we always use standard for a general enterprise. How to create a transport zone? So here's the steps we can in which we can configure the transposon, but spend time. Sorry, just want to mention, or just it's worth noting that you have to plan on transposon ahead of time. So transposon, definition of the transposon or configuration or transposon is very important for the whole system to operate. So just plan on it ahead of time. Oftentimes, we can use a default transposon in NSX 3.0 or 3.x. 3.x, we have overlay default transposon. We also have VLAN transposon default, two default transposon you can use. You don't need to customize or create your own transposon. But if you love to, if you want, you just create your own transposon and rather to use the default ones. And also mention that if you look at the configuration of the edge node, oftentimes we have to create a uplink transposon, uplink TC. Uplink TC, you can create a uplink TC for only for the edge node to form the uplink connections up to the physical router. Okay, now let's talk about the uplink. So there are a lot of terms we try to help you to remember them and give them a connection between each other. That means that we have to build some of the data structure or profile. We can include and connect a lot of discrete concepts into the one group or into the one profile. Here we talk about what blinks is, and also talk about the relationship with PNIC and lag. So if we look at the ATN, a transport node, definitely we have some physical connection or physical adapter. P1 is physical adapter, P1, P2, P3, P4. We have 4 PNICs, right? And on the top of that, we can create a lag for link aggregation. For example, we put a P1 and a P2 into the LAG group to form a aggregation, link aggregation. Here is LAG1 and yeah. So uplink, what is an uplink? Uplink is the logical interfaces of the NVDS or VDS with NSX. That means that here is there is a TN. We have a embedded NVDS or VDS with NSX virtual switch. So uplink 1 and uplink 2 is a logical interface on this specific switch, virtual switch. So uplink here does not do anything with physical layers physical P1 or P2, P3 or LAG. It's nothing to do with LAG and PX, P blah, blah, blah. So uplink just means it's a logical concept on a specific switch. This is one switch. We can see, let's draw another NVDS. This is NVDS2. Also, we can have the same name, uplink 1, uplink 2, uplink 1, uplink 2. So even it's the same name, but uplink 1 is specific for this switch, and this uplink 1 is specific to this NVDS2. That means it's a logical concept within a specific switch. So here's also an example. Uplink and PNIC and lag. We have to connect uplink to the PNIC and LAG or lag, right? There's a connection we have to deal with. So here's an example. We can assign uplink 1 to P3, just like this, to P3. We can assign uplink 2 to P4. We can assign uplink 1 to LAG, not a P blah blah blah, not a P blah, just LAG. We can put uplink 1 to LG or assign uplink 1 to LAG, which is a logical aggregation interface. Got it? I think you got what I mean. So, for example, here is also some 3 example. U1 means there's a uplink. U1 goes to P1, U2 goes to P2, U3 goes to P3, and etc. and so on. And the second example is uplink 1. Remember, this is the name for uplink. You can name it. You can give your own name for the uplink. There's a capitalized U and uplink 1 goes to LAG1, uplink 2 connects to LAG2. And the third one is uplink 1. Whole uplink 1 goes to whole LAG1, which include 4 physical interface. So you kind of like, there's a 2 concept and decoupled with each other. Okay. And further, just move on a little bit deeper to talk about teaming policy. So how the VM use this physical server, how these VMs use a logical uplink. So here we have a teaming policy come into play, and we have 3 types of teaming policy. For one is failover order, one is load balance, the second load balance or load balance source MAC. If we look at the failover order, you can see the VM for virtual machine 1, P1 is active adapter. It's primary adapter to go out, or just you should remember that V1 goes to U1 first. U1 connects to P1. So VM1 chooses uplink 1, then goes to P1 and go out. And the virtual machine 2, it is the same thing happen. It goes to U1 first, then in turn P1 and outside. That's the failover. That means if someday in the future the U1 uplink 1 failed, or P1, P2 failed, you can fail over to uplink 2 and leverage P3 and P4. The second teaming policy is load balancing policy. Load balancing means V1, for example, we have, sorry, we have two virtual machines. VM1 use U1, VM2 use U2 to go out and coming in. And for load balancer source MAC address, that means when you look at the load balancing mechanism, it relies on the MAC address, depends on the MAC address to load balance their traffic. For example, VM1 VM1 has a MAC 1, VM2 has a MAC 2, right? So MAC 1 goes U1, MAC 2 goes U2. This is the load balancer, round robin load balancing. And in another case, VM1 has two adapters. That means MAC 3, it has two MACs, right? MAC 1 goes to U1, MAC 3, my goes to U1, my goes to U2. That means the load balancing mechanism based on or per MAC address. There are just three teaming policies here for ESSi host. For KVM environments, only support failover. And also we have another supplement. We call it named teaming policy. Named teaming policy as a, can be used as a additional teaming policy only for optimization of VLAN backed traffic. And typically we use named teaming policy on the edge node uplink connection. So for example, here we have default teaming policy. We mentioned in the last slide. We have failover U1 as active, U2 as a standby. And we also have a storage teaming policy. This is a named teaming policy. That defines the failover order, U2 as an active link and U1 as a standby link. That means that for some specific VLAN, we use this policy. But for rest of the traffic, we use default policy. This is the difference in between. So for example, in this, imagine that here's illustrating that we have overlay segment, overlay traffic is following default teaming policy, and red traffic, this one, follow this storage teaming policy traffic. We can define which VLAN segment or which segment we can where we can use this named policy. Uplink profile. So now we have uplink, we have DZ, we have a lot of terms. So you want to put a lot of concept into the group to ease your whole configuration process. Here we have uplink profile. So in the uplink profile, we have we just put teaming policy in it. We have active uplink. We have uplink. We also have a connection. We just mentioned we have a connection. So logical uplink to physical interface or LAG connection relationship, and also have VLAN to transport VLAN for overlay traffic to traverse, and also have MTU. So we put a lot of factors into the uplink profile to give you a pretty simple datagram, pretty simple data structure for you to configure it easily. So also have a port mapping, port 1 to P2. Then we just, with this data structure, we have the whole logical structs here. We have NVDS, which is a virtual switch. We have a logical uplink. We have LAG if you have. We have a physical adapter or interface. Yeah, that's the whole struct. Yeah, that's a virtual uplink profile. Here, just give you some examples of uplink profile. So you can see here uplink profile, ESSI, teaming policy. We choose load balancer, soft spot. And we have active uplink U1, U2. We have standby uplink is none. We have transport VLAN is 10. Transport VLAN means you a VLAN where there's an overlay traffic. So many times we just think generally you have to configure a transport VLAN because you're going to use overlay traffic or overlay tunnel. Here's another example for KVM. It's the same thing. I think I'm gonna go over the whole terms and concept in the live demo in the next lesson. So you can just have here. You just have some touch on them, and we can go over the configuration and the user interface in the next lesson inside a live demo. So another things here I wanna point out that the network I/O controller or NIOC is a quality service or just relimiting feature. So here you can see that the important thing I want to mention or the NIOC is focused on the traffic type or bulk traffic type. For example, it's a management traffic, it's iSCSI storage traffic, it's a fault tolerant traffic, this is a virtual machine traffic, it's a workload. Workload traffic is your production traffic, it's a vMotion traffic, it's a vSAN traffic. So we just create a relimiting or create quality of service for a specific traffic type. Here we have a limit, reservation, and shares. I just put three definition here for you to refer to. Simply put, just remember NIOC is focused on the specific traffic. You can see here. If you want if you want a quality service, which is focused on a specific virtual machine, you have to use another one, which I talked about later. Here we have another segment profile or switching profile. Formerly we call switching profile. Segment profile, they are 5 types of segment profile or switching profiles. What is segment profiles? Segment profile is a layer, just pretty similar to physical switches, layer 2 security. Remember, if you're familiar with Cisco 29 or 3500, you just you have a port security, you have IP discovery, you have DAI, DHCP snooping, ARP snooping sort of things, or you have some BPDU guard, right? Just remember these features. A segment profile is similar to this feature on the physical switches. So here we have, for example, we have security profile. They just cover some DHCP read limit. We have a QoS profile. This QoS profile is focused on the particular VM traffic. For example, for the specific traffic you coming in, or ingress traffic or egress traffic, you can define their minimum bandwidth or average bandwidth, burst, and the peak bandwidth. This is for specific virtual machine or specific virtual NIC, in turn map to a specific VM. Right? So this is the quality of service profile. And we also have IP discovery profile that covering the RP function or DHCP snooping for the things, and the MAC management, MAC learning, and some of the MAC learning limit. Also has spoof guard. So we have totally we have 5 different profiles. So just remember here we just I summarized the 5 profiles and what they're about. I just give you the feels of them. Here we create a segment. We created a NVIDIA's and a lot of data structure mentioned before. And when we finish doing the whole project, we have a topology. We want to show us. We want to show the customers, or a kind of like a pane of glass for the operation and maintenance. So here the network topology that NSX gives you. So here we can, for example, we just created the web segment, and in this segment we just attach 2 virtual machine. Yeah, so pretty clear, and just right click. You can have other context menu here, and you can click in into different parts to see and check the configurations. So here the summarize to for takeaway, and just we talked about a lot of terms in this lesson. I just give you, for example, uplink profile, teaming policy, just NVDS and sort of things. Yeah. So that's it for today's lesson. And in the next lesson, I'll just give you a live demo on those complex concepts. I also give you the steps and flows for how to configure these segment TZ or TN sort of things. So thank you so much for watching, and see you in the next lesson.